Hi everybody. Well, last time uh, we started the branch instructions of the 68 HC12. So we come to the fifth category out of the total 7 categories of instructions. Okay, right here. So, and we mentioned we branch or not. In general, it based on the flag bits, okay, or it based on testing the flag bits of condition code registers. So that's where it came to. So right here. So the condition code register, they're here. They're here. So we talk about these 80 bits. And we also mentioned what these 80 bits are divided into 2 different types. One, the 3 bits focus on hardware control. In general, they are not used in making a decision on branch or not. So they are called the hardware control bits. Then the other 5 bits, they are the real arithmetic and logical operation bits. So we have H, N, Z, V, and C. They are mainly used, okay, when we execute the branch instructions. So in other words, when we have branch instructions, CPU branch or not, in general, it checks these bits to see if this bit meet condition or not. Okay, meet condition or not, the condition specified by the individual instructions, by the individual branch instructions. So today we focus on what we will do a few exercises, okay, on these 5 bits of condition code registers. Those. Last time we talked about each of them, okay, how they work out. And then we will go to afterward, we do some exercises. Then we go to the detailed branch instructions. We have a large number of branch instructions. So we stopped here last time. Last time we stopped I stopped here on this example. So here this example shows the 2 instruction statement. And so at the beginning, we load the value 8A into accumulator A. So this transition says, so this one transition says, well, afterward, we finish this one, everybody knows. So if this is accumulator A box, here we go, we load 8A inside. So 8A is 8 bits, that's no problem, right? Yes. So box accumulator A9 contains 8A. Next one, so we added this value. We added the AA is another value. We added this value. Let me change to low. We added this new value AA to the value in accumulator A. And now we need to add the AA to 8A. So we need to add these two numbers together. So what? So after we added these 2 numbers, we should have new value saved in A. So make sure the new result is also saved in A. Yes, so when we do this operation, when we add these 2 numbers, so we have a new operation, we have new values. And then this new result, okay, we have what? We have the information was shown by the condition code register flag bits. And when we add these 2 numbers together, if the number is 0, then the Z becomes 1. When number is negative value, then N becomes 1. When you have carry, C is 1. When you have borrow, C is 1. So we asking, after we do this operation, what should be those bits? N, Z, V, and C. So let's do it. So the best way is what? The best way is to convert each of them in binary. So let's do now. So let's convert them binary. So first one is 8A. 8A is let's convert in binary. So here we have 1 0 0 0. Okay, this is A. This is 8. Then we have 1 0 1 0. That's for A. So 1 0 1 0. I like to leave some room right here. So to leave some room here. So half bar by half bar. So we add, make sure it's addition. make sure this addition, this is not a logic OR. But here we add, then we add AA. So let me show this number again. Let me show this number converted right here. A, so we have what? 1, 0, 1, 0, and then another A is 1, 0, 1, 0, right? Yes. Now let's add these two numbers together. So let me show you. So when we add them together, that's easy. 0 added with 0 is 0. 1 added with 1 is 0, but with what? With carry. Okay. But this carry does not mean this carry. Does not mean the C, the flag bit C of condition code registers 1. Condition code registers 1 only when we have carry from left from the bit 7. Now, so here 0 adds 0, 0, and with carry, here we go. This is 1. Then again, for bit 3, this is bit 0, bits 0, bits 1, bits 2. Now with 1, we come to bit 3. Bit 3, 1 add 1 is 0, again, 0, but with carry, right? Again, here 0 add 0 is 0, but with carry is 1. Then, here we go, 0 add 1 is 1. We know very well. 0 add 0 is 0. Then 1 add 1 is 0, but with carry. So here we carry, let me write down carry in a different color. So here with carry, here we go. Yes? Now turns out our result right here is what? Is 3, 4. So if you write on this one, if you have to write on this one in a like here we come to with 3 is 4 in hexadecimal. So in other words, when we come back here, we go 3 and 4 will be saved back to, we'll replace the old value of A, of accumulated A. So this value will be changed to $3, 4, excuse me, 4. Now, but our problem asks for, tell us after we perform this operation, what's the value of N, Z, V, and C. So then here, mean this is what we need to check. This is what we need to check very carefully. This one. So obviously, here we do have carry. You see, we have carry here, the green one here. We do have carry here. See, we have carry here. This is carry. So C definitely is 1. You have carry. Of course, you have carry from left to most bit, from bit 7. Okay, that's no problem. How about the Z? Z right here, I said well, Z is 1 only if the oldest value is 0. Only if the last result here we got like here 0, 0, 1, 1, 0, 1, 0, 1. If all this value is 0, in other words, if our result is 0, 0 in hexadecimal, then the Z is 1. Here it's not. Here our value is 0, 0, 1, 1, 0, 1, 0, 0. It's not a 0. So the bit Z is 0. The bit Z is 1 only if our result is all 0. Even no matter you have carry or borrow. Okay. Now, but if Z is 0, if Z is what? Is 0, and also if our value is not a 0, then let's check to see if it's negative value or it's positive value. So that will tell us what should be the flag bit N. So I said what the N is negative. The flag bit N is means what? Is negative value. That means what? If the N is 1, if a result is negative value. Otherwise, N is what? Is 0. Let's check out our value. Here we go. Our value is 0, 0. Is 0, 0, 1, 1, 0, 1, 0, 0. So if we consider this is a sound number, if we consider 0, 0, 1, 1, 0, 1, 0, 0, it's a sound number. So it left most bits 0. See? This bits is 0. See? Let me show here. This bits this bit is 0. That indicates if we consider this number is a sum number, so it's positive. So for a sum number, is positive if leftmost bit is 0, and is negative number if leftmost bit is 1. So here this number leftmost bit is 0, so it's positive number. It's positive number, so it's non-negative. That's going to, if non-negative, then n0. 0. So now we already finished the 3 flag bits. Only one left is V. Let's see what's the V. So I mentioned last time 4 cases. Okay, 4 cases. Okay, 4 cases will make a V to 1. So in 2 cases we have 2 cases for addition and 2 cases for subtraction. For addition, I mentioned when we add 2 positive numbers, if our result is negative. So I mentioned for addition. Let me write it here somewhere. Right here. For addition here we add 2 positive numbers if result is negative, or when you add 2 negative numbers, okay, if result is positive, that's going to cause what? That's going to cause V to 1. Now let's check it. This is the only for addition. Okay, for subtraction we have other two cases. So let's check now. We are doing addition right now. We can check here. Now if we consider the 3, 4, and 8 are sound numbers. So if you check the leftmost bit of these 2 numbers we added here. So check right here. So this next number is 1. This making this number 3, 4. If we consider this is some number, so it's negative number. No problem. Same thing for a second number. Leftmost bit here is 1. That means this number is negative. Now we are adding here. We're adding 2 negative numbers. Okay, so we come to this case. We added 2 negative numbers. So let's check our result. Okay, if a result is positive, that's going to make a V to 1. So why in that case will make a V to 1? Because adding 2 negative numbers. If the result is positive here, that's not reasonable. There's something wrong. So that's called a overflow error. You add in 2 negative numbers, the result should be negative. But here it turns out it's positive, because that's some computational overflow error. That's going to make a V to 1 to tell the program there's something wrong. So let's check the V. Let's check the sum. Our sums come here. It's become 0, 0, 1, 1. No matter we have carry or borrow, we don't care about the carry bits. Carry bits are already taken care by here, or taken care by here. Here we go. So let's check our result here. This one and this one. It's 0, 0, 1, 1, 0, 1, 0, 0. That's what? That's positive. Because it's leftmost bit here. Because it's leftmost bits right here. Let me change different color. This bit is 0. Leftmost bit is 0. That tells us this number is positive. So they come to this case, positive. Adding 2 negative numbers here, you got positive. So added 2 negative numbers, you get positive. That's make the V to 1. So V here is 1. So this green part, V is equal 1, C is equal 1, Z is equal 0, N is equal 0. So in other words, after we execute the machine code of these 2 instructions by CPU, okay, after we perform this operation at this time, after the ADAA, after we execute the machine code of ADDA and $$ AA, then V is 1, C is 1, Z is 0, N is 0. Now, the following is ADDA. if you have branch instructions. Okay, we branch or not at that time. Okay, in general, the what it's best on checking one or more of these bits, or best on check one or more. The combinations of these bits. So that's it. So let's take a look at one more example. This time what? Because I assume you guys understand very well. So I only simply show you the operation, and we did not put these numbers in the instructions in the program. So it's very easy. But this time what? We take a look at the two examples about subtraction. Here we go. We consider 7/5 subtracted by D3. So let me show you here. So let me show 7/5 here, so part is better. So 7/5 subtracted by D3. So let's convert in binary. That's easy, right? When you convert binary, this is equal 0, 1, 1, 1. That's 7. 5 is what? 0, 1, 0, 1. It's no problem. Then subtracted by D3. Subtracted here, let me show the sign here. Subtracted by D3. D is equal 1, 1, 0, 1. 1, let me show you again in blue. 1, 1, 0, 1. D. 3 here is 0, 0, 1, 1. Right? Yes, now we do subtraction here. Again, let me draw a line here to show we do what? Half byte. I don't know why it didn't come out. Let me show you the red one. Okay, anyway, but I think you guys understand very well. So for subtraction, I hope you guys still remember that. In general, we involve what? We involve borrow. So let me show you. Let me use the red color here to show you. Yes. So let's do what? Let's do bit by bit. Let's do the subtraction from bit 0. 1 subtracted by 1 is 0. That's no problem. Then when we come to bits 1, 0 subtracted 1 is not enough. We had to borrow. We borrow from the next high odd bit of 1. So next high odd bit 1 is right here. Immediately we have what? 1 in bit 2. Bit 0, bit 2. So we borrow from here. Borrow from here we go. That's going to make the 0 to be 2. Because here we have what? We have 0, 1, 1, 0, 1, 0, 1. This 1 right here is equal to 4. Equal to 4. When you borrow here we go, you borrow 4. You borrow 4, that's going to what? That's going to make what? You borrow 4, but this is only 1 here we go. You borrow 4, but you subtracted only by this 1. Okay, so you should have 2 left. Right? You borrow 4, it's subtracted by 2. You have 2 left. When you 2 left, here we go. That means what? This bit is 1. Don't forget, okay? This bit is 1. Okay, make sure that when you borrow from high odd bit. So here you borrow 4. You borrow 4, you subtract by here's 1. This 1 corresponds to 2. So 4 minus 2, you still have 2 left. So this result is still 1. Now we'll come to bit 3. Bit 2. This bit 0, this bit 1, this bit 2. This here 1 is already borrowed by bit 1. So it's 0. 0 minus 0 because. Yes, then we come to bit 3. 0 subtracted by 0, 0. Then we come to bit 4. 1 subtracted by 0, by 1, 0. 1 subtracted by 0 is 1. 1 subtracted by 1 is 0. Then we come to bit 7. Bit 7 here is 0 subtracted by 1. It's not enough. Let's borrow. Borrow from who? Borrow from what? From the carry bit. We borrow from carry bits. Let me use different color. Borrow from carry bits. When we borrow from carry bits, this can make this here to be true. Okay, here's to be true. So 2 minus 1 is 1. Same idea right here, because when you borrow from, same idea come here. Something come here. When you borrow from this 1, this makes this bit to be 2. 2 times about 1 is 1. Right? But if you try to explain in decimal, that means what? You borrow from here 1, here this bit is what? Is the bit 2. Let's get 4. 4, this bit corresponds to in decimal equal to 2. So 4 minus 2 is 2. So 2, that's in decimal. But if you show in binary, this make this bit to be 1. Same idea when we come here we go. When we come to leftmost bit. So the bit 7 is not enough, so we borrow. When we borrow that make it what? I carry bit to be 1. We borrow from that bit. Or we borrow from bits 8. But okay, right? That's we can only borrow from carry bits. Okay, carry bit same thing as borrow bit. So borrow from here. That's gonna make this bit what so to be 2. Because 2 right here, 2 minus 1 is 1. Okay, so if you try to explain this one in hexadecimal, when you borrow from here, you borrow 1 bit here. You borrow what? You borrow from what? That's what? That's value is what? Is equal to twice of this value in decimal. So when you subtract this value, you still have half. Still have this bit left. So still 1 left. Let me change back this to 0. So always make sure in subtraction 0 subtract 1 is 1, not 0. With borrow bit. Borrow bit same thing as carry bit, so carry bit is 1. So carry bit is right here, show this 1. Make sure this is 1. After you just subtraction is 1, not 0. So now, if you check our value here, we go, what's our values? Our value become 1 0 1 0 0 0 1 0 as A and 2. It's A right 1 0 1 0. This is what? 2. But now, if so, let's see how our bits, how our condition code register bits are they're affected. For sure, here we have C is equal 1. Because we have borrow. Borrow is a special type of carry. So here, C. Let me write it here using different color. Let me add this purple. C here is definitely 1. See, with these bits. But how about the Z? Z surely is not 1. Because our value here is what? It's not 0. So I'm talking about this value is not 0. It's 1 0 1 0 0 0 1 0 is equal to A2. It's not 0. If 0, this should be equal to 0 0 0 0 0 0 0, but it's not. So that's going to make Z to be what? To be 0. Only if the all value is 0, all bits are 0, that's going to make Z to be 1. Z means what? 0 bit. Means what? If our result is all 0, that's going to make a 0 to 1. It's not. So, right here, let me show you. So, Z is 0. How about the N? N, here we go. I mentioned what? If a result is negative number, if this number right here is negative number, then that's going to make N to 1. Otherwise, N is 0. N means what? N comes from negative. The first letter of negative. Only if after we do subtraction, if our result is a negative number, then it's 1. I mean, only if we consider that number all number assigned. So here are numbers 10, 10, 00, 10. That's definitely 1 because it leftmost bits here. Because it's leftmost bits, right? Let me show this bits is 1. So that makes what? Negative to be 1. It means what? Because this is 1, that means this number is negative number. This is 1. So it's 1. And it's also 1. But let's check the flag bits V. Here we do subtraction. Last time I mentioned that when we do subtraction, then what type of operation we make the overflow bits to be 1. I mentioned for the subtraction, that again similar to addition, two cases. Let me show here. When we do subtraction, when we subtract the what? A positive number from a negative number. So when negative number subtracted by a positive number, result should be negative number. But you subtract a positive number from the negative number, then it should be negative. But if it turns out if our result is positive, that's going to make a V to 1. Another case is what? When we subtract the what? A negative number from positive number. When we subtract the what? A negative number from positive. This is already positive. We subtract a negative number. That's equal to we add a positive number. So our result should be positive. But it turns out it happened if our result is negative. Something's wrong. Like you subtract what? Negative 2 from 5. So that's equal to 5 subtracted by negative 2. That's equal to 5 plus 2. Should be 7. Should be positive. But if a result is negative, that's also cause all these cases will cause what? Will cause V to 1. All these cases will cause V to 1. V to 1. So now let's check it. Here we go. We subtract from 0, 1, 1, 1, 0, 1, 0, 1. This means what? This says what? This number here is positive, right? Yes, it's negative number. Then this number 1, 1, so a second number is 1, 1, 0, 1, 0, 1, 1. That's negative. The leftmost is 1. Top one, the first number is 0, so it's positive. So positive minus negative, here we go, right? Okay, let's check to see. So we come to here. We come to a second case. If the result is negative, that's going to make a V to 1. But let's see our result. Turns out our result here is what? It's 1, 0, 1, 0, 0, 0, 1, 0. That's negative number. That's why that appears here. V is 1. It's negative number. So we subtract a negative number from a positive number. It turns out our result is a negative. Here ends 1, right? You see, because this bit is 1. This bit is 1. Is negative. So we subtract a negative number from positive number. Turns out our result is negative. So we just meet this case condition. That's going to make a V to 1. So this is what our result for this operation. So V is 1, Z is equal to 0, C is 1 because we have borrow. Make sure when we have borrow is similar to carry. And N is also 1 because our result is a negative number. So that's our second example. Let's check what our last example here. So let me try to cleanse all this out so we have a little bit more room. So let me clean all of this. Yes, clean this so we can leave more room to it. But we still leave those actions right here. So now The example 3 is we do subtraction from A3 minus by D0. So I want you guys to try first. You try now. So let's convert each of them one to binary first. So let me show here. So we have, let me use this color. A3 sorted by D0. So let's convert the binary. Here we go. A, we have 1. Let me write it. This color is better. We have 1, 0, 1, 0. That's A. 3 is 0, 0, 1, 1. Subtracted by D0. D is 1, 1, 0, 1. 1, 1, 0, 1, right? 0 here is 0, 0, 0, 0. Subtraction, right? So let me draw a line here. This A right here come to this one. This 3 come to this one. Okay, yeah, let's show you half by half. Let me draw some other colors. We're doing half by half by. Now let's do subtraction. Let me use the red color here. So 1 divided by 0 is 1. 1 by 0 is 1. 0 by 0 is 0. 0 by 0 is 0. Let's come here. 0 by 1, we borrow from here. Borrow from here, that's make it 1. Because as I mentioned these algorithms. Then when we come to the base 5, this one already borrowed, so it's make 0. So we have here here we have 0. We already borrowed here like 0 bits. So 0 by 0. That's 0, right? 0. Then 0 by 1. 0 by 1, here we go. Again, we do same thing as we did for bits 4. So borrow from here. Borrow from here. That's gonna make this bit to 1. When we count the leftmost bits, here's what at the beginning is 1, but we borrowed it. So this bits becomes 0. Now we do subtraction from 0 by 1. It's not enough, so we borrow from leftmost bit. We borrow from bit 8. So bit here we don't know what's bit 8. So that's gonna make what? We borrow from carry bits. That's gonna make our carry bits here to 1. Borrow from here. That's gonna carry bits to 1. So then what? So similar to this algorithms, that's gonna make this bits to 1. Different color here. But don't forget, here we go. We have what? We have borrow bits. So it turns out our result here is, let me show here. Here, the result here goes D3 in hexadecimal. Now let's check our bits here. Let me run it here. Let me run it here using different color. Let me use purple again. Here obviously carry bits is 1 because you have borrow. C is 1. Z here of course is what? Is 0 because here our value is not a value is D3, it's not 0, 0. So Z here we go is 0. Z only is 1 if all value is 1. Let's check N. N right here we go. Okay, the leftmost bit of a number is 1 here. Is here 1. Let's make n to be 1. To be what? To be 1. The leftmost bit is 1. That means this number is negative number. Make n to be 1. Let's check what the flag bits v. Here we go. We do subtraction now. Yes. When we do subtraction here, we check this number is, and the first number is 1010. Here is negative number. Yes. Second number also is negative number. A result is also a negative number. That's reasonable. You subtract a negative number from another negative number, you got another negative number. So that's everything is reasonable. So that sounds right. So also, if you check our algorithm here, if you compare algorithm to here, you go, we see only 2 cases when we do subtraction will make what? Will make the v to 1. Is when we subtract a positive number from negative number. If you get positive, that's not case. That's not case for our problem. Or when you subtract a negative number from positive number, you get a negative number. That's not case here. Here, all numbers in our problem here, they are negative. So that's everything's good. So we have no overflow error. So when we have no overflow error, the flag bits v is equal to 0. So now in this case, what? Okay, v is 0, c is 1, z is equal to 0, the n is equal to 1. So this is our case for our problem. Now, and if you forgot the subtraction, the operation, okay, I hope you guys you get back to the end of the book you reviewed. Now, according to my teaching experience, some of our students are not so clear when we do subtraction. So let me erase this whole slide and show you some ideas. So that may help you guys a little bit. So let me clean all of this out. So because that you guys still have records. So let me erase all of this. Let me show you about subtraction. We mentioned a moment ago, when we do subtraction from 0 by 1, that's going to make it 1, but with borrow. Yes, let's call it borrow here. Borrow means carry bits is 1. But now let me show you. Assume now we do 4 bits. We do an 80-bit subtraction. Assume now we have numbers something like this in boundaries. Let me show you. Assume now we have something like this: 0, 1, 0, 0, 0, 0, 0, 1. Let's do it this way. If you subtract this number from, assume now we have number, yeah, let's call it this way. Let's call we have 1, 0, 0, 1, 0, 0, 1, 1. Let's do this way. Assume now we have this subtraction. Let's see our result. So half byte for half bytes. Let me put it. This half byte, low old byte. This high byte. So let's do subtraction. Here 0, 1, 1, 0. It's no problem. Here we come to bits 1. This is bit 0, right? Yeah, this is talk about what? Bit 0. Let's come to bits 1. When we come to bits 1, here we go. Bits 1, here we go. Number top here with 0. Here's 1. So that's not enough. We need to borrow. I mentioned so we come here and here. When you borrow, I mentioned we can only borrow from the next high order bit 1. High order bit, which must be 1. But you subtract here about 1, next bit you can borrow it on is 1. You can, so another words, when you borrow, you only have to borrow from 1. But let's check this bits. So let's try to borrow here. We try to borrow from here, that's not enough, because here is 0, bits 2. Then let's check what, bit 3. 3 also 0. That's what? That's nothing to borrow. I mentioned you can only borrow from 1. So let's check bit 4. Bit 4 is also not enough. It's 0. We cannot borrow from here. Let's check bit 5. Not enough. Nothing to borrow because they are all 0. We have to borrow from next bit what? 1. So let's check bit 6. Here's 1. That's good. Let's borrow from here. Borrow from here. So we borrow from this bits. When you borrow from this bits, that's going to make this bits to be 0. But as I mentioned, here we go. This bits they are much higher order bits. After you borrow from here, we go. Okay. This bits is what? In decimal is greater than all the bits we can add here. Right? So that's going to, if you borrow from this one, you borrow from high order bits. Here you borrow 2. But this bit right here is what? Here this is 8, this is 16, this is 32, this is 64. This is 1 and 2 and 4, 8, 16, 32, and 64. That's going to make all those bits to 1, 1, 1, and 1. And also this bit is also 1. Okay? Yeah, like we see here. Okay, now let's check it. Now let's check this bit. So in this case, what? Okay, now let's continue. Here, this 1 bit says become 1. This 1, this 0, this 1. This 1 is 1, this 0. This bit, this 1, 1. This 1 is 1. This 1 is 0, this 1. Here, this is 0, 0. Right? 0, 0, 0. Then we come to our leftmost bits. 0. 0 to 1 is again is not enough. So we have to borrow from what? We have to borrow from carry bits. So that's going to, we have to borrow from bits 8. That's going to borrow from here. When you borrow from here, we go. You make this. You make here we go. This bits to 1 too. Right? Yeah, correct. Let's make this bits to 1. You borrow from higher bits. As I show here, this algorithms. You make here is 1. This bit is 1. Borrow. So this make what? This bit to 1. And with carry bits. Carry bits is carry bits. Here is borrow. Okay, like this. So make sure when you borrow, you can only borrow from the what? 1. You can only borrow from the next high order bits 1. If the bits next to you is not 1, then you check what? The next bit. Then you continue to check until you find 1. If you got all 0, then you borrow from carry bits. So that's like what? That's like what? Like this. Let me show like this. Assume now, and now let me erase this. Assume now, yes, come here we go. Assume now this number is also 0. Now when you borrow, then what happened? We try to borrow from here, not enough. Even when come to the leftmost bit 7, it's still 0. We had to borrow from these bits. When you borrow from this bit, that's going to make all these bits to 1. All these bits to 1. I mean, yes. All these bits to 1. And this bit is also 1. Now and then what? If you do operation here, let me show in different color here. Well, when we come to this one, here's 1. This is 0. Make sure this is 1. This is 1. You want 1 sub 0. This is 1. Because all these bits already become 1s. All become 1s. Why? Because of what? Because you borrow from the highest order bits. This bits what? This bits here we go, when we convert in decimal, is even greater than total summation of all these bits. Like when we come to the bits 8, this 8, this 4, this 3, this is 8, this is 4, this 2, this 1. Even though you added this bits 2, bits 1, and bits 0 together, you can only get 7. Bits 4, 1 is 1, is equal 8. Like those, like I remember showing, so now we have 1 0 0 0, and then you compare this number. This equal what? 8 in decimal. But if your number is called 0 1 1 1, so you have all these bits are 1s. That's only equal 7. Right? Like this. So this number, because many different squads, they come from here. Now, if we do a subtraction, assume now we do subtraction from 8 and 7, but let me show you in binary. We do subtraction here. Now what happened? So 1 0 0 0 1. Of course, our result should be 1 in decimal. It's no problem. But now let's do the what? Let's do it in binary. Here we go. We come here we go. So here's 0 1. 0 1. That's not enough. Then let's try to here. Here this is not enough. This is 0. This is not enough. We cannot borrow. We can only borrow from leftmost bits, which is bit 3. This bits. Yep, this is the only one in high order bit than the bit 0. There's nothing we can borrow from here, from bits 1 and bits 2. We all had to borrow from bit 3. So then we borrow from here. That's going to make this bit to 0. When you borrow from here, from the point of decimal, you already borrowed the 8. You check this 1. If we say we only have 1 left here, we only have 1, which is 1 0 0 in binary. You borrow these bits. So you borrow all 8. So okay, you borrow all 8. So you make this bit to 0. Then let's make it what? This number becomes 0 0 0 0. So you borrow everything. You borrow 8. When you borrow 8, here we go. When we do the subtraction, so we have to convert. Here we go. You only borrow 1. Why you borrow 1? Okay, because you just have to subtract what in bits 0. So when you borrow 8, here we go. You have to convert all these bits to 1 and 1, and as a result is also 1. So all the 0 bits between the current bits you are doing operation and the bit you're borrowing have to be 1. Result is also 1. Now let's check what. Let's continue to do our subtraction. Let's come to bits 1. This bits 1. This bits 0. This is bits 2. This is bits 3. We have bits 0, 1, 2, 3. It's 4 bits. Now we come here. Let's come to bits 1. Bits 1 is 1 subtracted by 1. It's 0. Come to bits 2. Here we go. 1 subtracted by 1 is 0. Let's come to bits 3. Bits 3 here we already borrowed. So this is 0. This is 0. So 0. So no borrowing from additional bit. No borrowing from bits 4. So our result becomes 0 0 0 1. Okay, which is equal to 1. That's correct. It's 1. Okay, so don't forget when we borrow here, when we borrow last bits, the rightmost bits right here is because the bits you are doing subtraction now must be 1. It's not 0. So you see here, if you write on this 0, then you're wrong. If you write on 0, then your result becomes 0 0 0 0. That's wrong. 0 0 0 is equal to 0. Equal to 0 in decimal. A subtracted by by 7 should be 1. So don't forget what the bits you're doing subtraction now, okay, should be 1. Okay, good. I think that's pretty much enough for the subtraction and addition, and for our exercises on these 4 flag bits. Now all this this exercise will be very important. And I want everybody to know this because they are the key, that fundamentals of branch instructions. So now let's come to the branch instructions. As I mentioned last time, the branch instructions, they're very important. Okay, they're very useful in writing a program. They're in general used to what? Implement a loop or if then else the program segment. And in general, when it runs, they cause the program flow to change when condition is met. So how we can change when condition is met, okay, then our program counter value will change, will not be sequential anymore. So a program counter will become a new value somewhere in a different memory location where our machine code is stored. So CPU it goes to there to fetch the machine code. That's how we branch. So we may branch backward or forward. Remember when we discussed the time clock cycles in section 4.5, I mentioned about in general, okay, when we fetch machine code from memory, okay, address the sequential, unless we have branch. Remember I mentioned that when a branch, okay, we jump to a different location memory, we fetch machine code from there, okay. That's not sequential. The branch is very important, especially when we write a quite long program. Okay, when you have branch, okay, let's make a loop that we make our program to be much more efficient. It turns out that the 68H12 has 2 different type of branch instructions. Okay, so one is unconditional branch. Another one is conditional. So the conditional branch, okay, the conditions mainly based on the CCR flag bits, mainly based on the condition code register flag bits. So these are mainly based on bits. That's why the conditional is also called the bit conditional. The mainly check these 4 bits. Remember, I show you these 4 bits. We have N, with C, with Z, and V. They mainly test on the values of one or more the condition code register flag bits, these bits. If condition is met, if defined condition met for instruction, then it branch. If not, you don't branch. Now, for the conditional branch instructions, okay, it's also further divided into short branch and long branch. The short branch and long branch. So let me simply tell you what it means short branch, what it means long branch. Short branch means what? Assume now, okay, our program counter value right now at a particular point here. Short branch means what? I said, well, you can branch backward or you can branch forward, but the location you can branch to is quite close to you. It's quite close to where you are now. So where is a distance, but the point you branch to is very close to where you are now. Short. For long branch, that means what? Okay, if you are here now, the place, the new location you can branch to, you move your the CPU, you move execution to there. It's quite long from you. In general, you can go anywhere you like out of the 64K baud memory, which contains all machine code. So main difference between a conditional short branch and conditional long branch is how far you can branch to. No matter it's short branch or long branch, all the branch instructions They use relatively address mode. So we didn't talk a lot about the relative address mode, okay? But we mentioned something about that. So when we say relative address mode, that means what? That means the operand of an instruction in general specifies to as what? A new location, relatively away from here. Or we simply call it what is offset value. So the operand will be offset value. And you should add this value to the current program counter value. That tells us a new location in memory where we should go to fetch machine code, to fetch what? Fetch the machine code of what? Of instructions. So it tells us what? Relative distance away from here now. So this relative address mode can in general, this operand can be specified using a numerical value. Okay, when we say numerical value, that means what? Can be any, can be decimal, can be binary, can be whatever. Or if you don't know this numerical value, okay, we can specify this operand using one label. So when we say label, that means what? Okay, when we discuss the instruction format, we said what? When you run some program, you can label it. So you can use that label what in whatever the new location is specified as operand of your branch instructions. Well, some people what they even specify the branch. They even divide the branch instructions in different ways. And some branch instructions can even belong to more than one category. So that way, somebody divide branch instructions. What we have like this, we have like a they call unary branch. Unary branch means what? Means what? Unconditional. And then somebody divided, they even have simple branch. Some branch is simple. An unsigned branch and signed branch, these two parties pair. Signed branch, unsigned branch, that means what? That means the what? Offset value. You can add it, so that's what your operand in a branch instruction can be negative or can be positive. So when that number is positive in decimal, then you branch forward. You branch to a memory location which has higher address than the address you fetch machine code now. If it's unsigned, if it's signed, that means what? That number can be negative or positive. Can be positive or negative. When unsigned, that means always positive. For the signed branch, here we go. If number is negative, if offset value here we go, if offset here, or called what? Operand is negative, then you add a negative number into the program counter value right now. That's going to make what? You branch backward. You branch to a new location, okay, whose address is what? Is lower what you have right now. That's called what? Signed branch. For unsigned, we assume it's always positive, because that means all numbers specified here as operand is positive. So make sure that when we say the unary conditional, the unary branch, that means one unconditional. So here I give some detailed explanations. The unary branch is although top branch, but it is unconditional, always execute. We'll talk a little bit more. Simple branch means what? It takes one specific bit. Okay, in general, a single bit. In the condition code register, it is what? In a specific state. as the previous operation. You check only a single bit. So that's quite simple. That's why I call it simple branches. Unsigned branch here, okay, that means what? That means what? We check what? A result based on unsigned comparisons, unsigned quantities. So the numbers we involved is unsigned. The taking one comparison or test of unsigned quantities result in a specific combination of condition code registers. So we do some operation, these numbers, they must be positive or 0. Same idea for the signed. That means what? When we branch not, we check what? We check the condition code register bits. But those bits, they are what? They come from a comparison or test of signed numbers. The numbers we involved in previous operation are signed. So let's talk a little bit more about each of them. So let's start from short branch. Okay, when I mentioned short branch, okay, I said well that means where you can branch to is quite close to. Then the new location where you should go to fetch machine code from memory. Make sure all the machine code are programmed there and stored in memory. When CPU try to run this program, okay, CPU need what? Fetch the machine code from memory first. So you have to know where you go, you fetch. Remember, if you recall what we discussed in lecture 4.5, I show you what happened between memory and condition code registers, okay, in different time clocks. Okay, yes. So all machine code, okay, when we run a program, they are in assembly language. But when we try to assemble the converted what? Each of your program into machine code, including the machine code for instructions and the machine code for the operands data. They save everything in machine codes. Then after this is only assembly process. Okay, CPU is not involved because it's done by assembler. Then when we try to run a program, CPU have to go to memory to fetch the machine code of this assembly language program instructions. Then after you fetch, you decode. After you decode, then you take action. So when we talk about the branch right now, okay, that means what? We assume we already have all machine code in memory. But when we come to machine code of a branch, then because we need a branch, we need to go to a different location to fetch the what? Fetch machine code. How far you can go away? How far you can go there? You fetch. How far is your new location, which contains our machine code, comparison right now? That's determined by what? By the offset value. For short branch instructions, the offset value tells you the new location, okay, is on 8 bits, signed 8 bits. So when CPU runs the program, here we go, we simply need to add this signed 8-bit offset value to what? Current program counter value. Find out what's that new value. Then we go to that new location, fetch machine code, and execute. So we have new location. So add the current offset value to the current program counter value, tells us a new location. For short branch, okay, the new location should be quite close to here. So the offset value is only 8 bits, but it's signed. So the leftmost bit is a signed number. So in this case, when we convert this signed offset value to binary, to what? To decimal, the range is from -128 to +128. And if you represent this number in hexadecimal, it's from A0 to 7F. This is equal to 127. This is equal to -128. So in other words, the numerical range of the short branch offset value, okay, from what? From the address of instruction immediately following the branch one is this. So in other words, what if you stay here right now? If this is what the program count value after you finish the branch instruction, but before we go to the new location, make sure this after immediately following the branch instruction, not ahead of it, not before the branch instruction. After you finish the branch instructions, where we should go now? That means to tell us where we branch to. Then you added the offset value, which can be specified using which is nothing but the operand of your branch instruction. That's offset. So you add this number to the program counter value after you finish the branch. You add there. That will tell you a new location it goes to. So the number we can add to in decimal is what is negative 128 and positive 127. So that's quite close. In total, it's only about what? So it only spans 256 locations, including yourself. That's quite close. In comparison of a long branch, the offset value is 16 bits, standard 16 bits. In this case, that means what? You can branch much far away. So when we convert what in decimal, it ranges from negative 32,668 to positive 32,767. So this range total, when we add them together, is equal to 65,536, including yourself, including your current location. That means what? This range of long branch covers everything of total 64K bytes memory. Make sure I told you guys the total size memory is 64K bytes. So if you use long branch instructions, the offset can be so long, can be ranged from 800 to 7FFF. That can make you to branch anywhere. So long branch model in general used when a large displacement between decision-making steps are necessary. Okay, another word. You guys hear about you need to jump much further away, including both for forward, the backward and forward. That's why number sometimes negative, sometimes is positive. So main difference between short branch and long branch is what how far you can branch to the way. For short branch only 127 locations forward and negative 127 backward. So let's go to see all these detailed branch instructions. Let's start from what? First one. Here to show you. Here you go. Unary branch, the unconditional branch, the always branch. Even though it's called branch, but conditional is always true. We have two. BRA is always branch, always, and BRN, branch never. Branch never means what? We never branch. Conditions never met. This is what we see. The conditions never met. One is never equal to 0. So it's always no. Always no, branch, never branch. First one, branch forever. Branch always, no matter in most cases, is condition always true. Branch always. But those make sure those are short branches. So when branch, we can only branch to this location, away from you. This is only offset value. We need to add this value, whatever the value given. This is only range. Okay. When you branch here, when you have instruction, your program should always have a given offset value for your branch instruction. So you add this given value to the current program count value. Make sure when I say the current program count value, that's the value after executing the branch instruction itself. So we come to the operand of branch, not the branch instruction itself. So for branch instruction, we have opcode and operand. I'm talking about what the program counter value after the opcode. Now the second one is what? The second one is branch never. If branch never, that means what? It means what? We never branch. Why we use it? In general, this one is not commonly used in programming. Okay. In general, it's used for debugging process. Sometimes you hope to do some test. You use branch never. So those are short branch, also unary branch, unary short branch. Let's come to short branch, but the simple branch. They have condition. The conditions what? They have condition here. The simple branch. Condition only check a single bit. Only check the conditions only a single bit. So let's check them. We have branch if carry clear, BCC. If carry clear, carry bits is C. If you carry bits clear, that means C is equal to 0. So that means what? If C equals 0, we branch. Where we branch to, that depends on the operand. What's the operand? That's what offset you specify by itself. The program specify. You can specify this offset as numerical value, or you can specify as label. As one label of other instructions of your program. If so, when branch, it will branch there to execute that instructions. So we have carry clear and carry set. Carry set means C is 1. And now is what here? If you have some number, here we go, then what? In this case, CPU will check what's the flag bit C. If it's 1, it will branch there. If it's not 1, here we go, it will not branch there. We have BEQ, branch if equal. This term is used quite often. Branch if equal, that means when equal is when we compare something. That means Z is equal 1. Because our result is what? Is 0. When you do subtraction between two numbers, if they're equal, our result is 0, all zeros. That's going to make the condition code register Z to 1. And the branch MI, branch if minus. When branch minus 1, you do subtraction, the value is negative value, means 1. If so, you branch. BNE is right here. Branch if not equal. If not equal, it means we compare two numbers. They're not equal. The result is not 0. So Z is equal to 0. And we have branch if plus, a branch if overflow clear. Overflow clear means V is equal to 0. Means we have no overflow error. Then let me show this one. This one's branch if overflow set means if V is equal to 1. So sounds like probably we may consider this two like a pair, and this one is pair, and this one's pair, and this two is pair. But anyway, you keep in mind all this offset here must be shorter, all these operands or offset must be short. Must be range from 128 to from negative 128 to 127 right here for this offset. No matter you specify in decimal or is binary or hexadecimal, that's what we see here. For the branch, this range, see? Now, if you go to the book, here we go. So if you go to the book, here we go. We see BCC. That's on page 542. If you check this simple short branch instructions, if you check all of them there, you see they all runs relative address mode, nothing else. But here we mentioned it only runs what in the relative address mode. That means what? The operand is offset value. We have to add this offset value into the program counter value following the opcode of your branch instruction. That will tells us what? A new location. new relative from here, relative address mode. So if you keep back to page 542, right here we see these branch instructions at the end of the table. We see BCC and the BCS and like those. And then we see the BEQ. BEQ is on BEQ. Branch is not equal. Seems it's not shown here. Yeah, BEQ right here is the one following the BCS, and also we see BGE, and yeah, this too. BGE is not a simple. BGE is not a simple instruction. BGE, well, right, if you check the BGE after the BEQ on table on page 542, BGE check both the flag bits N and the V. So it's not a simple branch. So it's not shown here, it's shown what in next table. So anyway, I'm trying to tell you for all this the rounds, if you check the table here, either on page 542 or on page 543. Okay, like a BNE and those B, and we have the BVS and the BMI, yes, BMI, BNE there, and BR, BVS, BVC, they are shown on page 544. These two are shown on page 544. For all of this, if you check the address mode, they all runs in the relative address mode. And they also tell us what's the condition. So if you check for each of them, if you check the second column on the table operation, so on one hand they tell us what it's about. On the other hand, it says what they give us condition if the v is equal to 0 or if the v equal 1, like a BVC what a branch if the flag bits v is equal to 0, BVS if the flag bits v is equal to 1. Like here I show you those, but they also give explanation in second column of the table there. Now also I want you pay attention for all of this branch. They don't affect the condition coded register flags. The only branch, they do not do any test, they do not do any operation, they do not perform any logical operation or the arithmetic operation. That's why if you check a BCC, a BCS, all of this, okay, they never affect the condition coded register flag bits. They only test and then branch to. They never perform any operation. They only test and go there or not. So this is what a simple short branch. You see, this is a simple branch. And also short. Short means what? The where you can the branch to only this location, specified by this field. Also, they're simple. Why simple? Because they only check what? One bit condition. So that means what? For some branches they are not simple. They check what? They check a combination of more than one bits to see if the condition is met. Here again, a short branch, but unsigned. Unsigned branch means what? We assume all numbers here we compare or we do or assume now those conditions they come from a result of unsigned operation. So I like to start from what? From the second one, BHS. Branch if higher or same. When you compare two numbers, if they're unsigned, that means what? We assume all numbers are positive. Unsigned. If branch if higher or same, that means what? If C is equal to 0, if no carry, no borrow. Okay, no carry, no borrow. That's going to what? That's condition for BHS. Upper specify right here, but again, it's short range. From 128 to 127. This is C. So BHS means what? If branch is higher, the same. When you compare two numbers, okay, this number when you compare, as mentioned, you only do subtraction. If higher, okay, then what? We don't borrow. We don't borrow. The C is equal to 0. Or when we do subtraction, if the result is 0, that means what? The same. The same means what? The C definitely is 0. That's going to be branch BHS. Branch if lower, if not higher or the same, then it must be lower. That's going to make C to be 1. That's where we branch. We use BLO. C is 1. Okay, this. Then if branch higher, then what? Then branch higher here we do not include same. It must be higher. Then we OR the bits C and Z together. Make sure this is OR condition. This is OR, not addition. Okay, it's 0. If the OR, if all two bits like C and Z together is 0, then both must be 0. C is 0, Z is 0. Yes, if you remember, I mentioned about it. If all two numbers are result is 1, as soon as one of them is 1. If here result is 0, that means what? The both must be 0. Same thing we come to here, the branch of lower same. Branch lower the same, that means what? So we use BLS. That means if all the C or Z together is 1. That means either C is 1 or the Z is 1. And they both can be 1 too. When both 1, we still meet our condition lower or same. So so if C is 1, Z is 0, that's fine. If C is 0, Z is 1, that's fine. If C is 1, Z is 1, that's also fine. Anyway, these are conditions we had to meet. We have to meet. This slide shows what the 4 instructions. They are about the same. They correspond to and I mean they're signed. They're signed. That means what? Those bits value like N, O, or V, Z, they come from operation of signed numbers. When we do comparison, when we do arithmetic operation, these numbers are signed. They have signed numbers. Here you see we check what? We check for all of them. We check what? More than 1 bits. Here we go. We have the BGE. Okay, is what? When we do XOR with N and V, it's 0. When we do XOR, that means either N is 1, V is 0, or the N is 0, V is 1. This, but this one does not include 1, 1. If 1, 1 XOR, that's equal what? That's equal 0. So if this case, if this 1, 0, that's not going to make it XOR to be 0. So if V is 1, V is 0, this is not going to branch. It branch only if greater than or equal. Or if N is 0, V is 1, is not going to branch. So only when both the N and V are 1, or when both N and V are 0, that's going to make this to be 0. That's going to branch. So this branch if greater than or equal. Then if only have greater than, then we remove. Then what? We have taking care of what? The condition of Z. So when you also OR the Z together, if you still have 0, that means Z here is also 0. That means what? It's not. That means what? Is what? Here we do not include equal. So it's only if greater than. So this is 0, but here we go. The opposite of what? The opposite case of what branch if greater than is branch if less than or equal. If less than or equal, then it means what? Okay, when we OR the Z together with the XOR N and V together is equal 1. That's going to branch. We call it BLE. Next one is the branch if less than. Is what? We conduct what? XOR between N and V is equal to 1. When number is less than another number, that's going to make it what? Either N is 1, then make it V to be 0, or the N to be 0, V is 1. Okay, in this case, what? We will branch. So if you go to the table, if you check all of them, okay, the condition is clear. If you check BGE right here is on page BGE yes, is also on page 542, and BGT and BH and BLE is show up on page 543, and BLT, all this then runs what? Okay, it gives very clearly. Okay. About the machine called relative address mode, different things. So all these are pretty much, they are short branch. See, all these are short branch. Even what for this unary branch, short branch. This what simple branch, also short branch. This what this unsigned branches, they are also short branch. And this signed branch also short branch. In other words, what all here we go. The operand are in the range from -128 to 127. Yes. So now in comparison, we have long branch. So we have same pair of long branch for each of the short branch. We just went over those. So we have a short branch, we have shorter under branch, we have long under branch. So it's very easy. We simply add a L ahead of what? Ahead of the short branch. We have BRA and BRN. We added a L ahead of it. Ahead of it. We have LBRA, LBRN. That's long branch. And long branch. Conditions same. Conditions same. Conditions all the same. The only thing is what? Okay. The only difference is about the range. The offset value is much greater than what do we have now. This is what long simple branch. Simple branch, everything condition the same. Here we go, only 1 bit. Everything the same. Everything the same as that one. The only thing is what we add here, we add 1 here. We add L here. We add L ahead of each of them. Here, add L ahead of each of them. Let's make long branch. Condition the same. Then we have unsigned branch. That means what? This is what come from unsigned operation. Come from operation between unsigned numbers. It's the same as the one. We add L ahead of it. This is where this L comes from. Long branch unsigned. Unsigned right here. Unsigned here we go. Long short branch. We have 4. Same idea. We have 4 here. This is our condition. This condition also given, as I mentioned, they're also given in a book and in second column. So if you go to page 548, you see this long branch at the bottom. We have about like more than 20 and like about more than 10 of them. You see, we have what? We have the condition, they're very clear. They all runs relative address mode. This long branch in general, they involve a little bit more time cycles. So check right here. If you check this long branch, you see well most of them they involve maybe 4 time cycles or 3 time cycles. But if you compare the short branch, a lot of them involve 3 cycles or sometimes even 1 cycles. Or even like what? Yes, most of them involve 3 cycles or 1 cycles. But long branch involve 4 cycles or 3 cycles. They're much longer. Yes, that's where you could find the way. Then we also have the long signed branches. Signed branch. Okay, all these bits come from signed operation. Come from operation of numbers that are signed. And it's okay, similar to the short branch, we only added L here. BGE, BGT, BLE. If you check them, BGE dot here. We add L ahead of each of them. Conditions absolutely the same. Only difference is what? If offset. Long branch. So by this, we come to the end of lecture 12. And so we mainly focus on the discussion of branch instructions. And of course, we also did a few examples for the condition called register flag bits, and I show you about how these bits come from. This lecture is very, very important. And when we move forward, we will see the branch instructions are very, very useful. Also, make sure we have another homework. I want you guys to start working on this. That the problems 4 and 5 are challenging part of chapter 2. I want you guys to try. So that's pretty much we have for lecture 12.